Or what's your full name?
Rosenbaum.
Is that correct?
Yes.
Just changing the name in here so people don't think you're Biostat Support Services. Okay. So we've got the audio going, then we're just going to use the computer mics. And take that from you. Split this. First try. Which topic is it? And just so we don't forget it, because you just moved it to the desktop, right? You made a copy
Yeah.
there. So I'll go ahead and I'll eject your thumb drive so we don't forget that. This. All right. You screen. Perfect. Here. Big screen. Good floating meeting controls. That's out of the way. Minimize that guy. Just that very discreetly in the bottom corner. And there you go. Is there anything else? I have a clicker if you'd rather use that. Yeah, we can just fix that. Perfect. Let's go.
So, what do I do? Page down?
So just arrow keys here. I think that works too. Those are page up, page down.
This would do too? Okay.
Yeah. So I think down, right, and page down all are gonna advance. Left page up, are gonna go back.
Okay. Perfect.
And the mic is currently the podium mic is muted. We can. Oh, it's good. Should give him a nasty feedback right there. This also doesn't seem testing. Okay. Seems to be good to go, but this isn't controlling the volume for some reason. Is not. Usually this. It's all kind of just the same, but it is loud enough, so I think it'll be good. That for you. Yes. That's good for you. And I'll just do that. Kind of hides the controls and just makes it a copy of this screen. So, good. And then whenever you're done with this, I have to jet back up and go do some more work with my coworkers. Whenever you're done with this, if you just want to leave the laptop and the charger in that office that you've been sitting in 314, and I'll pick that up some other time.
Okay, so it won't be locked because I can't lock.
Right. I'll be around. I'll be in my office. So, but if for some reason I'm not. If like right when you go out the door of your office, my office is right on the other wall with like a glass window on the other side of the printer, but it's just right on the corner. Yeah.
Okay.
So, ready. Yeah.
Well, actually, I can't speak for sure. Something about that. I just your dance. Not for everybody. Yeah. No, we're not.
Hi, everyone. Welcome to the joint biostatistics and statistics seminar. And it's great to see everyone here. Today, we are very, very honored to have Dr. Paul Rosenbaum here speaking at the seminar today. Really, Paul needs no introduction, but still take some biography from the website. Paul is the Robert Posel Professor Emeritus in Department of Statistics and Data Science at Wharton School of the University of Pennsylvania, where he worked from 1986 through 2021. He is pioneer of a lot of topics in causal inference in observational studies, including sensitivity analysis, optimal matching, design sensitivity, evidence factors, quasi-experimental devices, and with Don Rubin, the propensity score. And Rosenbaum is authors of several books, 5+ books, and all of them are phenomenon books, including observational studies, design of observational studies, and many others, which are highly, highly recommended to everyone. And without further ado, welcome, Paul.
Thank you, Ting, and thank you for having me. I'd like to talk today about being realistic about unmeasured biases in observational studies. And I hope what I mean by that will emerge as we go along. An observational study is a study of treatment effects when we can't run a randomized experiment. Treatment and outcome may be associated in an observational study, even if the treatment has no effect, precisely because treatments weren't randomly assigned. We always adjust for measured covariates, but that often is not enough. There may be unmeasured covariates that need to be accounted for. That is, without randomized treatment assignment, the probability of treatment may depend on relevant covariates that were not measured, including the potential outcomes. This is the main source of controversy in observational studies, and therefore it organizes the design and the analysis of observational studies. The talk has an example, some methods, some theory for design and analysis. So in thinking about unmeasured biases, context matters. The talk uses a very simple example, almost a toy example, in which the context is familiar to everyone. I'm going to make a few quick claims about how observational studies should be designed if they are to have greater insensitivity to unmeasured biases. The proofs of these claims are in my design book. I'm going to spend more time showing that the choice of methods of analysis has a substantial effect on the degree to which a study is sensitive to unmeasured biases. Perhaps surprisingly, even if there is evidence of unmeasured bias, that may make the study insensitive to larger unmeasured biases. That depends on the context. The example has several control groups, and so I'm going to spend a sentence describing the logic of several control groups. The talk is loosely based on a few items. It is one of the two examples in a book that's supposed to appear this summer by Springer. I have a few general theses I'd like to persuade you of. The first is that every observational study is affected by unmeasured biases, but that fact is not debilitating. The studies of smoking and lung cancer were clearly affected by unmeasured biases, and yet we are completely confident on that basis that smoking causes lung cancer. So the presence of such biases is not the relevant concern. It's whether they alter the conclusions. Unmeasured bias is unmeasured, but it often has detectable consequences. The detectable consequences may heighten or diminish our concern that the ostensible causal effects are spurious. A sensitivity analysis talks about unmeasured bias, but it is computed from, it is a function of, like an estimator, it's a function of the observable data. If I change the distributions of observable data by changing the study design, I change the sensitivity to unmeasured biases. The same thing happens if I change the methods of analysis. Without guidance from statistical theory on previous point, it's easy to make poor decisions in design and analysis and report that your results are sensitive to small biases when that's actually just a mistake in the way the study was either designed or the analysis was conducted. So this is the example. Again, it's a toy example. It's about HDL cholesterol and light daily alcohol consumption. So you often hear it said that a daily glass of wine each day prolongs life, reducing cardiovascular mortality, perhaps increasing HDL cholesterol levels, the so-called good cholesterol levels. A recent position paper by the American Society of Clinical Oncology, the major clinical cancer group, is sharply critical of this claim, emphasizing that alcohol is a carcinogen, that it increases the risk of death from cancer, and they also point to risks from accidents, liver diseases, and violence. So that's the issue. Purely as a methodological example, I'm going to look at a small corner of this, alas, not the most important corner, but I'm only using this to hang the statistical theory on it, namely whether light daily alcohol consumption increases HDL cholesterol. The data are available to you if you'd like it in the weighted rank package, so you could reanalyze the data in various ways. We're going to look at adults age 20 or more in NHANES. At this time, NHANES and CDC define binge drinking as 4 or more drinks on an occasion for a woman, or 5 or more drinks on an occasion for a man. It's more or less the same as legally drunk, although one is a blood alcohol level and one is the amount you consumed. So we're looking at people who don't do that. They are drinking between 1 and 3 alcoholic drinks on most days, meaning at least 260 days in the last year, and they had a median of 520 drinks in the last year. We have 3 control groups. The first control group is group N for never. They had fewer than 12 drinks in their life and a median of 0 drinks in the last year. Control group R had more than 12 drinks in their life, but fewer than 12 drinks in the past year. They never had a period in their lives when they engaged in binge drinking on most days. And these 2 also had a median of 0 drinks in the last year. And finally, there's control group B for a former binge drinker. These are people who had a period in their lives when they engaged in binge drinking on most days, but stopped and currently drink, if at all, on at most 1 day a week. And they had a median of 4 drinks in the past year. So I'd like you to take a moment and think about people in each of these groups. You probably know people in each of these groups, and think about what else is going on in their lives, right? Because what else is going on in their lives are the unmeasured biases that we're talking about. We have 406 blocks of size 4. That's the 406 daily drinkers in NHANES, and 1 person from each of the 4 control groups. They were matched for age, sex, and education. Of course, there could be a lot of other variables that we would be reasonably concerned about. They were also matched for a discounting feature in NHANES. NHANES doesn't collect everything on everyone, so they take a random sample of people and they collected methylmercury for them. So the blocks are matched for whether you're in that sample. So some blocks have 4 people who have a methylmercury measure, and some blocks have 4 people who don't have a methylmercury level. The bottom part is showing you how the matching changed things. The daily drinkers were mostly men. The N and R groups, never and rarely, were mostly women. The former binge drinkers, again, were mostly men. The matching corrected all that. The daily drinkers were a bit older. The matching corrected that. The daily drinkers were a bit better educated. So a 4 here means some college, about 2 years of college. So on average, the daily drinkers had a 4. And the N, R, and B were more like high school. After matching, they're more similar. What's this business with multiple control groups? So this is my sentence about multiple control groups. Campbell and Bitterman had the idea that maybe that there's a variable that's unobserved, but even though it's unobserved, I might be able to find groups that are very different in terms of this variable. I might know the groups are very different in certain ways, even though I don't know the value of the variable. So I could find groups that systematically vary this variable. And as a consequence of varying it, I get to see what happens as I vary it. If it doesn't do very much, then it can't be a big source of bias in the comparison of treated and control groups. You notice that the study omits people who have milquetoast doses of alcohol. It doesn't include anybody who drinks twice a week, right? They're out of the study. So that's one of the tactics for increasing insensitivity to unmeasured biases in observational studies. If there's a dose-response relationship, the optimal number of people to have, so far as insensitivity to unmeasured biases, who have milquetoast doses is 0. You do a calculation and it says the best number is none of them. You don't want any of them. Be different in a randomized experiment without bias. Those people would tell you something without bias. But if there is a bias present, they tend not to have a big enough effect to demonstrate insensitivity to unmeasured bias. And they're actually hurting them. Blocks of size 4 are better than matched pairs. So we're looking at 1 to 3 blocks. In what sense are they better? Well, think about what would happen in a matched pair if you were looking at an effect of alcohol. An effect of alcohol would raise HDL cholesterol for the drinker and leave it alone for the non-drinker. And so you'd see many pairs where the daily drinker had higher cholesterol levels than the control. What would a bias look like? Well, I'd have 2 observations from the same distribution because there's no treatment effect. And then somebody calculates the order statistics and tries to give a higher probability that the person with the higher order statistic is in the treated group, and that looks the same, right? So that's a deficit of matched pairs. But 1 to 3 blocks are better. Why are 1 to 3 blocks better? Because in every block, in the absence of interference between units, in every block, the treated person is being hit by the treatment and is raising one response, one person in the treated group. If I sort 4 observations from the same distribution into order to get order statistics and try to push the larger ones into the treated group, it actually has a different appearance. That different appearance wouldn't be apparent if you looked at one block, but if you looked at many blocks and used a statistic that was alert to this possibility, you would find that the results are insensitive to larger biases in blocks of size 4 than in blocks of size 2. And I'll come back to that and show you that later. We also have an unaffected outcome, methylmercury. So the World Health Organization and CDC say that almost all exposure to methylmercury comes from eating fish or shellfish. There are occasional accidents where people are exposed to it otherwise, but it affects very few people. People who've looked for methylmercury in alcoholic beverages have not found even trace amounts of it. So we have every reason to doubt and no reason to believe that alcohol is causing people to have a change in their methylmercury level. And the question is whether we can use that. So this is what the data look like. We have, remember, daily drinkers, never drinkers, rare drinkers, and former binge drinkers. Their age distribution is about the same. Their education is about the same. And in the last panel, you're looking at HDL cholesterol, and it's somewhat higher for the daily drinkers. If we compared the 4 groups in all 6 possible pairwise ways, D versus N, D versus R, and so forth, using Wilcoxon signed rank test and corrected for multiple testing using Holmes procedure, we'd find that group D is higher than all 3 control groups. The maximum p-value for those comparisons after adjustment is 10 to the minus 16th. On the other hand, the control groups do not seem to differ from each other. The minimum p-value comparing control groups to each other is 0.21. So what does that tell us? Doesn't tell us much. It tells us it's not chance, right? What we're looking at on the right side could be an effect of alcohol. It could be some bias in who chooses to drink, but it's just not chance. Do you think these people are living similar lives? So my first thesis is every observational study has unmeasured biases. So what we're looking at here is some other NHANES question. Have you ever tried marijuana or hashish? Among daily drinkers, 73% said yes. Among never drinkers, 9% said yes. Among rare drinkers, 25% said yes. Among former binge drinkers, back up to 75% said yes. Have you ever tried cocaine, heroin, or meth? 29% of the daily drinkers said yes. 4% of the never drinkers said yes. 4% of the rare drinkers said yes. And 37% of the former binge drinkers said yes. What about methylmercury in your blood? It tends to be higher among the daily drinkers, suggesting what? It's suggesting they're eating more fish, right? That have different diets than the people. And that's actually directly relevant to cardiovascular fitness, their fish consumption. Have you been to the dentist in the past year? 67% of the daily drinkers said yes. 48% of the former binge drinkers said yes. Tell me there is somebody in this room who is surprised by this, right? You knew this as soon as you thought about what was going on in the lives of these people, right? You knew that something like this was going to happen. This is going back to methylmercury. Remember, the blocks are matched for whether you have a methylmercury measure. So there's 200 blocks where everybody has a methylmercury measure and the other group people don't have one. On the left, we're looking at HDL cholesterol. You saw that before, but now I've merged the 3 control groups. On the right, you're looking at methylmercury levels, right, where we don't think there's a treatment effect. So we're wondering, is there a treatment effect on the left side? And we're pretty sure there isn't a treatment effect on the right side. And it's somewhat distressing to look at that picture because they look a lot alike, right? So we'll come back to that. I'm going to introduce a little notation. This is probably familiar to many of you, so I'm going to go through it a bit quickly. We have treatment indicator, whether you're a daily drinker or not, Z. Causal effects are the potential outcomes under daily drinking and not. We observe one of the 2 potential outcomes and not the other. So this is the Neyman-Rubin notion that causal effects are comparisons of potential outcomes under alternative treatments. The outcomes may be multivariate. Here they may be both cholesterol and methylmercury. We have some covariates that we've measured, age, sex, education, and we're obviously worried about unmeasured covariates. What's a randomized block experiment? It involves putting together people who look the same. Look the same means there's some function of X, and they're the same on this function of X. And then I flip a four-sided coin, a little hard to imagine, but you get the idea. Flip a four-sided coin to pick one person to be the treated person. That coin is fair. What does that mean? It means that the behavior of the coin doesn't depend on the potential outcomes. Or stated a little bit more formally, treatment assignment is ignorable given the observed covariates if 0 is less than the probability of treatment given X and the potential outcomes, and that equals the probability of treatment just given the observed covariates, and that's less than 1. So that's saying that treatment is independent of potential outcomes given observed covariates. If treatment assignment is ignorable given observed covariates, then appropriate adjustments for X in a wide variety of senses suffice for causal inference. It becomes a technical statistics problem, not a problem that has special features. We often speak of ignorable given something else. So we might say ignorable given some function of X because I don't want to adjust for all of X, or I might say it would have been ignorable given X and an unobserved covariate. My whole problem is the fact that I don't have this particular unobserved covariate. It would have been fine if only I'd had U, the unobserved covariate. In that expression 1, there's a familiar guy. He's the probability of treatment given the observed covariate. He's the propensity score. And a familiar fact says that 1, ignorability given X, is sufficient for ignorability given the propensity score alone. So that we only need the one scalar guy to adjust for measured biases. The other guy is also familiar, and he has a name. He's the principal unobserved covariate. He's the probability of treatment given the observed covariates and the two potential outcomes. He's unobserved. Why? Because we never jointly observe both potential outcomes. We never observe this guy and cannot estimate him directly. Suppose he's always between 0 and 1. Well, then two key facts follow. The first is treatment assignment is ignorable is equivalent to saying the propensity score is equal to the principal unobserved covariate. That's just a restatement in English of 1, right? 1 says that. The second fact is that treatment assignment is always ignorable given any function of X and the principal unobserved covariate. It doesn't matter what function it is, could be the function that throws away the observed covariates. So what is that saying? It's saying the principal unobserved covariate is the whole ball of wax. If you had it, you could do causal inference. If you don't have it, you can't do causal inference, right? So he's the whole ball of wax here. It's important that he's a function of the potential outcomes and the observed covariates. So he comes into existence almost immediately after the Neyman-Rubin causal inference structure. I build I blocks. We have 406 blocks of 4 people, one of whom is treated. So the sum of the Z's in a block is 1 for every block. We imagine this is built in the following way. We sample observable quantities in the population and assemble them into non-overlapping blocks. That is to say, we decide to match for some function of the observed covariates. This function of the observed covariates is the same inside a block, but varies between blocks. Our worry is what? That these blocks are not adequate. Their blocks are not adequate in the sense that they haven't controlled for the principal unobserved covariate, even though I've controlled for H of X. This could happen in 3 ways. Controlling for the observed function of X might not control for the propensity score. Second possibility is that controlling for H of X didn't control for the principal unobserved covariate because it's not the treatment assignment is not ignorable given X. And the third possibility is that both of those are true. There's bias because they did a lousy job of adjusting for the observed covariates, and there's also bias because it wasn't enough to adjust for the observed covariates. There's also unobserved bias. Let's write calligraphic F for the potential outcomes and observed covariates for the people in our study. The principal unobserved covariate is a function of F. Let's write calligraphic Z for the possible treatment assignments. So a possible treatment assignment is an I by J matrix of 1s and 0s, and there's 1, 1 in every row of this matrix, right? That's indicating who got the treatment. There are J to the I such treatments, and calligraphic Z is the set containing those matrices. We've sampled people in such a way that we ensure that the actual treatment assignment is in calligraphic Z. And I'm going to represent that by conditioning on that fact. And I'm also going to abbreviate conditioning on the fact that the treatment assignment has one treated person in every block by just conditioning on Z. That'll make formulas look a little bit tidier. In the simplest case, in a randomized block design, every one of those probabilities is 1 over J. The principal unobserved covariate in a randomized block experiment is 1 over J. I want to get from the principal unobserved covariate in the population to what's left of the principal unobserved covariate after I've done the matching, because that's what's really important, what's left of him afterwards. So let's start by thinking, before we force the blocks to contain one treated person, let's just think about the chance that person IJ is treated, and we have the rest of those same people being control. What's the probability of that? That's the principal unobserved covariate for IJ times the product of 1 minus the principal unobserved covariate for the other J minus 1 people in the block. It helps to pull out the factor of 1 minus the principal unobserved covariate, so the product no longer changes depending on who we're talking about. If I then condition on the fact that there's one treated person in each block, right, by just ordinary conditioning arguments, what I got left as the piece of the principal unobserved covariate that's left after conditioning is theta IJ. And you notice that he's the odds of principal unobserved covariate divided by the sum of the odds of the principal unobserved covariate. These guys sum to 1 in each block because somebody's the treated person, conditional on Z. So this is what I said before. You can think about the sensitivity model in either of 2 ways. You can think about the population before we matched, and that says the odds of the principal unobserved covariate in a block controlling for X may differ by at most a factor of gamma. Or you can think about it in terms of what's left of the principal unobserved covariate after I match for H of X, and that becomes the ratio of the 2 thetas, the probability that IJ is the treated person divided by the probability that IJ prime is the treated person. Different statistics, different research designs correctly yield different levels of sensitivity to unmeasured biases. We'd like to understand this so that we can make wise choices in design and analysis. I'm going to do this twice. I'm going to first do it by analyzing the alcohol data, and we'll see something happen. I hope that piece is clear, okay, because we're analyzing a data set and something happened. Of course, it's not going to be convincing because we see something happen in one data set. We don't really know what's truly going on in one data set. So we're going to take the data set out and put in a probability model, and we'll see that what we saw happening in the alcohol data is exactly what you expect to see happening from the normal distribution or the logistic distribution or the T distribution or any distribution you might reasonably think of. I'm going to start with a collection of closely related statistics that include some familiar and some unfamiliar statistics, and we're going to see how results vary in this collection. So the collection is going to vary in one dimension. There's one thing that varies over this collection, from stuff that's familiar to stuff that's strange. The stuff that's strange is going to clobber the stuff that's familiar, okay? I could do this with other families of statistics. These are weighted rank statistics. We could get rid of weighted rank statistics and make them M statistics produce the same effect, but the story would just get complicated because multiple things would be varying. All we're going to do is vary the weights in the weighted rank statistic, but you could vary them in weighted M statistics or in anything else. We're testing the null hypothesis of no treatment effect. We rank the responses in each block from 1 to J. So who's got the highest HDL cholesterol, who's got the lowest, right? We write the right ranks as QIJ. That's the rank within a block. We also look at the range of responses, highest response in the block to the lowest response in the block, and we calculate him. We rank the ranges from 1 to I, there are I blocks, and then we divide by I to get a number between 0 and 1. You got a big WI when, if your block is very dispersed, people are very different. You have a block with small WI, if the block, almost everybody has the same HDL cholesterol. We take some function, this is the thing that's going to vary among the test statistics, some function phi of W, and it's going to score how stable the blocks are. The test statistic is I find the rank of the treated person in a block, I multiply it by its weight, and I add it up over blocks, and that's my test statistic. So you've seen this guy before in pairs, right? If J is 2 and the phi function is always 1, it's constant, then you're doing the sign test. So you've seen that before. If the phi function is the identity function, then you get Wilcoxon signed rank test. And for general phi, you're getting a general signed rank statistic, which have been studied for decades. If J is bigger than 2 and you take phi equal 1, you get the blocked Wilcoxon rank sum test. So this is Wilcoxon's other test. You calculate the rank of the treated person in the first block, add it to the rank of the treated person in the second block. Keep doing that until you get to I blocks. That's discussed in detail in layman's text. If you take phi to be the identity, you get what's called Quade's test. And Quade's test is the generalization of Wilcoxon's signed rank test to blocks instead of pairs. So here are 4 phi functions. As I say, the 2 familiar ones are going to get clobbered by the 2 strange ones. The first familiar one is the horizontal line that gives you the sign test and Wilcoxon's rank sum test. The diagonal line is the Wilcoxon signed rank test and Quade statistic. And then you have these 2 Cobra-like guys who have the strange names of U868 and U878. So they ignore small ranges, rise steeply, and then level off at the top. Anything that had these shapes would be fine. These happen to come from a U statistic, which has some additional nice properties, but we won't be thinking about those. U878 does more of what U868 was doing, ignoring the small blocks, the stable blocks. Very important set, B gamma, is the set of bias treatment assignments. So remember, theta is an I by J matrix of treatment assignment probabilities. They sum to 1 in every block, right? They're what's left of the principal unobserved covariate after I have conditioned on the fact that there's 1 treated person in every block. B gamma is the set of all thetas, all I by J matrices that satisfy the 2 constraints. One, that is a probability, they sum to 1. And the second is a sensitivity model for gamma. We have 406 blocks, size 4. So theta is 1624 dimensional. He's 406 rows, 4 columns. But he lives in a flat of dimension 1218 because the probabilities sum to 1 in each block. B is a closed, bounded, hence compact set of matrices. The sets are nested. If B gamma is smaller than contained in B gamma prime, if gamma prime is bigger than gamma, right? And in fact, as gamma goes to infinity, if you gave me any theta which doesn't have deterministic treatment assignments, 1 or 0 treatment assignments, eventually there's a gamma which will include it. So this is a yardstick for measuring thetas. It's not actually an assumption, really. So I just said that. A randomized block design has what? It has a theta equal to theta bar, where theta bar is 1 over J, right? So the set B1, gamma's 1, has just 1 guy in it, and that 1 guy is the matrix, which is always 1 over J. As soon as we get to a gamma bigger than 1, there are infinitely many matrices in B gamma, and it's not identified, and nor is the treatment effect identified. If we knew theta, we could do the calculations pretty easily, right? If we knew the principal unobserved covariate, we would know the probability that any particular treatment assignment arose, and we could calculate the test statistic when that particular treatment assignment arose. And if we wrote bracket A for the indicator function of an event, right? And we rejected the null hypothesis when our test statistic was bigger than little t, we could calculate the probability that we would falsely reject a true null hypothesis, and that would be this guy. So our whole problem is we don't know theta, right? If we knew theta, we could calculate the correct randomization-based treatment assignment probability. So we maximize that previous quantity over all theta in B gamma, all possible treatment assignment probabilities in this set B gamma, which is getting bigger and bigger. And we see at what point does that change the conclusions. So let's do this in an example. So we're going to try out our 4 test statistics, Wilcoxon, Quade, U868, U878. And we're doing this for the HDL cholesterol data. And we're calculating the maximum p-value that could be produced by a bias of magnitude gamma. So if you assumed that there are no unmeasured confounders, that's gamma equal to 1, right, a randomization distribution, all of the test statistics agree, no way you'd see those box plots we started with by accident in a randomized experiment. Gamma equal to 2, which is not a small bias, but it's not an enormous bias either. They're all in agreement. But notice something interesting happens at gamma equal to 3.5. Wilcoxon's statistic has petered out. The maximum p-value is now above 0.05. So small p-values are possible, but p-values that don't reject at the conventional level are possible. But notice Quade's statistic U868 and U878 are going strong, right? And they're just as valid as test statistics as Wilcoxon's statistic. At gamma equal to 4.5, the Wilcoxon upper bound is 0.74, whereas Quade's statistic has a p-value bound of 0.04. So it's about to give up, hasn't quite given up. At gamma equal to 5.5, U868 has just given up, right? At gamma equal to 6, U878 is still rejecting the null hypothesis, but it's about to give up. To put this in context, smoking and lung cancer is like one of the most solid conclusions from epidemiology that the field has ever produced. Hammond's study in 1964 is sensitive at a gamma equal to 6. Okay, that's very insensitive to bias, but it is sensitive at gamma equal to 6. You notice that here, HDL cholesterol and daily alcohol consumption is insensitive to a bias that would have invalidated smoking and lung cancer, but only if you pick the right test statistic. If you pick the wrong test statistic, you're back at being sensitive at 3.5, and the study is much more sensitive to unmeasured bias than it would be in smoking and lung cancer. We want to see, I want to show you the claim I made before that 1 to 3 blocks are better than 1-to-1 pairs. It's not fair to compare 406 1 to 3 blocks to 406 pairs because there's twice as much data in the blocks. So we need to equate pairs and blocks. Let's consider a Gaussian linear model, additive block effects, constant within block variance, calculate the mean of the treated group minus the mean of the control group, and I'll figure out how that behaves. If I have M 1-to-1 pairs, the estimator has variance 2 sigma squared over M. He's normal with that and the variance. If I have I 1 to 3 blocks, the estimator has 1 plus 1/3 sigma squared over I. I equate those two expressions and I find out 406 pairs is worth 207 1 to 3 blocks. The estimator would have the same variance and the same distribution, couldn't be more the same than that, right? So here we're doing the same thing for the data. On the left, you're looking at 406 pairs. Where did I get them from? I picked a random control from the 3 controls I have in each block, random control. On the right, I'm picking 271 blocks at random from the 406 blocks. This is an equitable comparison in the sense that under a normal model, I wouldn't care which of the 2 sides of it. But notice that in a sensitivity analysis in an observational study, you really should care which side of the thing you're in. If you look on the left, you're seeing much greater sensitivity to bias. So Wilcoxon's statistic, which was giving you a p-value at 3.5 in the vicinity of 0.05, is now giving you a p-value bound of 0.99. So the result is much more sensitive to bias. And you see that for all of the statistics. The statistics still vary, but there's much more sensitivity to bias on the left. On the right, what are you seeing? You lose 1/3 of the data. It's not a good thing, right? But it doesn't radically change the conclusions. It's about as insensitive as it was before, just a little bit less, right? The kind of thing you expect when you lose a fraction of a big data set, not a radical change in the conclusions. And again, this is not a unique thing for the data set. Can we understand all this theoretically? Suppose we had some model that generated the data and we had I blocks of size J, and we let I go to infinity. Could we understand theoretically in terms of a probability distribution, not a data set, what's actually going on here? So I'm letting I go to infinity. So every quantity we used to have now gets a subscript I telling you that it's been computed from I blocks rather than more or less blocks. I'm working under, again, a kind of linear model, conventional block model. I want you to think about a treated minus control person in the same block. He's kind of an atom, in this study, which has molecules, right? So the atom is, I'm going to look at one treated person in a block and compare them to one control in the block. And that's going to have, under this model, be a constant tau, the treatment effect, plus the difference of two errors, which are IID. I'm going to set the treatment effect, and I'm going to talk about him in units of the standard deviation. So this is one treated minus control pair difference, and tau is going to be that thing divided by the standard deviation of the same quantity. So tau is, in this case, a half at the bottom, and that's saying that the treatment effect is half the standard deviation of one treated minus control pair difference. That will allow us to compare different distributions, and we'll try out different taus. I'm going to start with the premise that the study is actually unaffected by unmeasured biases. So what you see is really what's going on. And this is the kind of situation in which you would like to say the results are insensitive to unmeasured biases. Actually, you'd like to say, I found the treatment effect. This is the treatment effect because there is no bias and there really is a treatment effect. But in an observational study, you don't know you're in this favorable situation when you are. The best you can hope to say is, I found a result that's insensitive to fairly large biases. So this is the alternative hypothesis. The null hypothesis says, no, there's no treatment effect at all, but there's a bias in treatment assignment of at most gamma. So we're now going to fix the power of this test. The test is going to distinguish that favorable situation of treatment effect with no unmeasured bias versus bias of magnitude gamma and no effect. We're going to say, make the power 90%. Making the power 90% and fixing a gamma, if I want to find power 0.9 with a particular gamma, there's a sample size and a level relationship. So perhaps I could have level 0.1 if I had 100 blocks, but if I had 406 blocks, perhaps I would have level 0.01. So the first situation is not good enough. I'd like to have a smaller level. The second one is a little better than perhaps I need. What do we want? We want alpha to go to 0 as fast as possible. As the sample size increases, ultimately the power you specified, 90% power, doesn't matter. You get the same answer for at this level of resolution for every power. There's typically a number called the design sensitivity, such that alpha is tending to 0 if the sensitivity analysis is performed with gamma less than the design sensitivity, is tending to 1 if gamma is above the design sensitivity. So on the left side, you're in the happy world that you're familiar with. P-values get smaller as the sample size gets bigger. On the right, you're in a nightmarish world. P-values get larger as the sample size gets bigger. And why does that happen? Because I'm becoming absolutely convinced that I can't tell this null hypothesis from that alternative hypothesis. I can't tell a treatment effect of a certain size from a bias and treatment assignment of a certain size. There's no way that's going to happen. So gamma tilde is the limiting sensitivity to unmeasured bias as the sample size goes to infinity. He depends on everything in sight, and we look at him carefully to figure out what's a good design. If gamma is less than gamma tilde, then the p-value is tending to 0, and the level of the test is tending to 0. There's usually a Bahadur slope, which is telling you the rate at which that's happening. So the Bahadur slope is telling you the p-value. The level is tending to 0 at an exponential rate with multiplier rho. The ratio of two Bahadur slopes is a Bahadur relative efficiency, and you can think about it in terms of relative sample size the way you do with other measures of relative efficiency. He's better than Pittman efficiency in observational studies. That's the usual asymptotic relative efficiency. Pittman efficiency lets the treatment effect go to 0. Guess what? An infinitely small treatment effect is always sensitive to an infinitely small bias. So you're not really learning anything useful by doing a Pittman efficiency calculation in this context. That's not so bad, actually. I mean, if in all the observational studies that were ever conducted in which there was an infinitely small treatment effect, we had always been unable to say anything. How much have we been unable to say? Nothing at all, right? And it's only really a treatment effect that's big enough so that we would care about it, that we really want to say something about it. And in that case, we really do have an opportunity to say that it resists biases of meaningful magnitude. So this is calculating some design sensitivities. It's calculating them with a treatment effect that's half the standard deviation of a pair difference. And it's calculating them for pairs and for blocks, and it's calculating them for Wilcoxon statistic, Quaid statistic, U868 and U878. So these are the limiting values of gamma that you can distinguish from this alternative hypothesis. And you see the pattern is exactly the pattern you saw in the data set, right? The statistics are in the same order, and blocks are better than pairs, right? You're getting a bigger design sensitivity for blocks. If you made the treatment effect a third, all these numbers would drop a little bit towards 1, but they'd exhibit the same ordering of procedures. If you made the error distributions T distributed with 5 degrees of freedom, you'd see essentially the same numbers. If you made the effects not constant but heterogeneous, so half the time the treatment effect is a third of a standard deviation and half the time is 2/3 of a standard deviation, and it averages out to half a standard deviation, the numbers would look essentially the same as they do here. So here we're looking at the bond or relative efficiency of procedures at gamma equal to 2. Why gamma equal to 2? You notice that all of the design sensitivities are bigger than gamma equal to 2. So every one of the statistics here has a fighting chance. The p-values are getting smaller for gamma equal to 2. If we were talking about a bigger design sensitivity, some of these statistics would have p-values tending to 1, and some of them would have p-values tending to 0, and we would have infinite or 0 bond or relative efficiencies depending on who's got the bigger design sensitivity. So the top half of this table is comparing a good statistic, U868, to a good statistic, U868, but it's comparing blocks of size 2, 3, and 4, and you're looking at relative efficiencies. The first row is 1 because it's the statistic compared to itself. You notice that you're seeing relative efficiencies as large as 3 in this table, right? So blocks are better than pairs. In the bottom part, you got the double whammy. I've made the wrong choice of test statistic. I got the wrong choice, and I did pairs instead of blocks. And there you're seeing relative efficiencies as high as about 25, right? Remember, 25 is heading off to infinity, right? This is not heading towards bigger. This is heading through the roof, right, as we change things. In statistics, we often get excited about a 10% or a 15% or a 20% improvement in relative efficiency. You're seeing a 2,481% improvement in relative efficiency, right? So this is something we should actually be reflecting on when we choose test statistics. I want to spend a couple of moments going back to the methylmercury part of this story. So remember, there's 200 blocks. We have the HDL cholesterol levels, and we were wondering whether that's a treatment effect. We're pretty sure what's going on the right side is not a treatment effect, that's bias in who chooses to drink. Right. It turns out, if you think about it, on the left side, we're not sure quite what we're doing. We're not sure when we look at a particular theta and we postulate a particular treatment effect, whether the treatment effect is the wrong treatment effect or I have the wrong treatment assignment probabilities. On the right side, we don't think there's any treatment effect. So what we're really doing is testing the hypothesis that the thetas are the randomization probabilities. So I do that little calculation and say, does this look like it came from a randomization distribution? And the p-value is too small to calculate from Quaid statistic and R. It just gives you 0, one of those tiny little zeros with nothing, no decimals. So it's not the randomization distribution. What should we make of that fact? To avoid doing lots of possible comparisons, I'm just going to keep using Quaid statistic. That's not the ideal thing to do. If you want to look in the paper, you'll see discussion of how you might do better than just always using Quaid statistic. Tests for bias should be different from tests for effect. But let's just keep it simple and do just Quaid statistic. Remember, we're changing a couple of things. We're only looking at the 200 blocks, and we're using Quaid statistic. The study becomes, the HDL cholesterol comparison becomes sensitive to bias at gamma equal to 3.614, 200 blocks Quaid statistic. That means there, for every theta in B 3.614, the p-value is less than or equal to 0.05. But if I sneeze and it gets a little bit change gamma, it's going to give me a p-value above 0.05. I do the same calculation for the methylmercury levels, and I find that I reject every theta that's in B 1.993. So essentially B2, gamma equal to 2. The bias is at least gamma equal to 2. The methyl mercury data is forcing you to believe that. Remember, I said that's not a small bias, but it's not an enormous bias either. Notice first that the sensitivity analysis doesn't require any amendment, right? It acknowledged that the study is sensitive to biases bigger than 3.614, and we're being forced to believe the bias is at least 2, but that's not making us change what we said before, because what we said before is still true. But actually, it's better than that. There's a part of B 3.614 that's troublesome, okay? These are the points in B 3.614, a set of biases, where if I sneeze, I get a p-value above 0.05, right? So that's a little corner of this big set of treatment assignment probabilities. We just tested no bias in treatment assignment. Theta is equal to theta bar, but we can test the points in this troublesome set. So let's test those points. So we test those points. And when we test them, we find all of the troublesome points, the points where we're about to become sensitive to unmeasured bias, have p-values of 10 to the minus 7. So what is the data saying? What is the methyl mercury data saying? You were worried about these points, but you shouldn't be. They're not remotely plausible. I reject them with a p-value of 10 to the minus 7. So in a sense, there's no gap between what we're seeing in the sensitivity analysis and the test for bias. As soon as the sensitivity analysis is petering out, the test for bias is stepping in and saying the things you're worried about are actually not things you should be worried about. Could we go further in this sense? Could we test every theta? Why don't we do that? Why don't we test every possible theta and collect all the thetas that are not rejected in a set, capital theta? From first principles, that's a confidence set for theta. It's all the thetas we don't reject. It's a funny confidence set because he's not consistent. He doesn't converge to a point as the sample size gets bigger. In fact, the dimension of theta is growing as the sample size gets bigger. So the problem is getting harder as we're gaining something. But at the same time, we are rejecting points in this set. So we might as well use that information. Some of the thetas are not plausible. A test for sensitivity analysis is informed by a test for biases. If instead of looking at all of the thetas in B gamma, I just consider the ones that are also in the confidence set that I haven't rejected. I don't have to worry about those troublesome points. I don't really have to worry about the randomization probabilities. They've been rejected. Let's just worry about the things that haven't been. So you notice that there are two p-values on this page. The bottom p-value is the one we were looking at before. It's the worst p-value in B gamma. The upper p-value is the worst p-value in B gamma intersect theta, intersect the confidence set. That's a smaller set. So a max over a smaller set is a smaller max. So this new p-value is never worse than the old p-value and might be better, smaller than that. If you do the calculations out, you find that P 3.614, the uninformed p-value, is 0.05, but P prime 3.82, the informed p-value, is also 0.05. So the smallest bias that can explain everything we saw is not 3.614, but 3.82, right? So this is an amplification which some of you will be familiar with. It just says the difference between 3.614 and 3.82 is not trivial. So let me summarize what we saw in this picture. We saw in this picture that the picture on the left is sensitive to a bias of 3.614. The picture on the right is sensitive to a bias of about, is rejecting any bias less than about 2. That doesn't require an amendment to the left side, but one of the things that's happening is that the smallest bias that can produce both sides of this picture is a bias of 3.82, bigger than the bias that's needed for the picture on the left. So we found evidence, very strong evidence of bias, and it only strengthened the causal conclusion. It pushed it towards insensitivity to larger unmeasured biases. Let me summarize. Unmeasured biases are present in every observational study, but they may not be debilitating. Statistical theory can avoid aiding in making mistakes that exaggerate sensitivity to unmeasured biases. My sense is that such mistakes are not only possible, but are likely. If you look at what we commonly do in observational studies, the one method that I gave you that's commonly used is Wilcoxon signed rank test for matched pairs, right? That you might actually see on a daily basis, and that was a big disaster in this example. Design sensitivity and Bondor efficiency can be applied to studying when a particular study design, a particular method of analysis will give us conclusions that are insensitive to fairly large unmeasured biases. Even when there's evidence of bias treatment assignment, it may actually increase insensitivity to unmeasured biases, strengthening the causal claim. That depends on the context. Sometimes it will strengthen it, sometimes it will weaken it, but in this example, it strengthened it. So let me close there, and I'd be delighted to have your comments and questions.
Yeah, so that's considered there is no, there is any bias, certain magnitude. So if we're going to when analyzing the data, that would follow in primary market that yield that smaller one. That tells that and so on, again, that we comparison comparing two extremes. One comparing the bias, the fairness, and those. Every one of them is computer effective in one line. The main reason for doing that is because in that situation, I know what I want. So the bias and there's no treatment effect. No one rejects another line. The treatment effect is no one identifies. The further reason was you said that there might be situations where both of these things are present, and the only problem with working with computer technique, the only problem with working with them is that don't quite know what you want. Right? If there's both a bias and treatment effect, you'd be discouraged if we had a trivial treatment effect and a big bias and found the treatment effect in that way. On the other hand, we also discussed if there was a big treatment effect and a trivial bias and hits the treatment effect. It's only the fact that you're not quite ambivalent. Yeah, so how with the other treatment, there is no treatment. There's a bias. I don't want to reject. Right. So you're protected from that by the sensitivity. Sensitivity that's saying in all cases correctly. You know, the chance of a bias this magnitude producing a small p value is a most something. So you're being protected on that side. It's like having a lot of tests. It's right. Action. No, so it's like in regular ordinary hypothesis tests in the sense that we promise that every value that is falsely rejects the probability of happening. Here, for every valid test in the presence of a bias again, it falsely rejects the probability of happening. So the promise is the same. That part is fixed on the structure of sensitivity analysis. And then the question is, what can I actually find with that wonderful promise? And some statistics do better at least against favorites.
Thank you. I also have a question. So the negative control outcome usage is pretty cool. Like it rules out impossible treatment assignments. But what if the scenario that the negative control outcomes, they are not like pure negative control outcomes, but they just have smaller treatment effects?
Right, so you could build that in. That would add up wrinkle of complexity, and you'd have to specify the magnitude of that effect. I haven't seen anybody do that, but we could, and it probably is a practical kind of a question.
Yeah. And also related to this, like if I have, for example, two negative control outcomes, technically, if they are not like pure negative control outcomes, so I can find like no possible theta that makes them
That's true.
feasible.
Right, so one of the things you could do is have this theta set depend on several tests for bias. And it is true that they might reject every theta, and it tells you something is wrong besides the presence of unmeasured bias, and that might well be that they aren't truly unaffected. Sure.
Other questions, especially from students.
I love questions. Nobody's asked me a bad question ever. Yes, thank you.
Thoughts like more towards the end of slide 3 or 4, we were bringing up, like we had mentioned that there was the one section was like between 1 to 3 drinks. And you would like remove basically everyone and I only had 2 drinks, so they were just 1 to 3. Is it basically saying that like the difference between drinking 2 drinks or 3 is negligible, but there's other factors specifically for people who have 2 drinks that's causing.
Okay, at the time I said that, I didn't have the tool I needed to say, answer that question, but we now have the tool, okay? The tool is that the design sensitivity is made worse by including such people, the people who drink 2 drinks, even if there's a dose response relationship, so they have an intermediate level of HDL cholesterol, including them, even in ways which acknowledge that they have an intermediate level. You're not dumping them in the group with. So, for example, there's statistics which give people weight, rank statistics which give people weight depending on the size of the dose they got. And those things increase power in a randomized experiment because there really is some information in the guy who has 2 drinks a week. But that information has a much lower design sensitivity than the information of the people who are drinking daily relative to the people who are not drinking at all. And so including those people in any way you do it just detracts from the design sensitivity. Actually, why don't I give you a different version of this for which I have a picture, okay? So this is addressing a question, which is, why do those Cobra-like guys look like they do? Remember, they're ignoring some people too. They're ignoring people who have small ranges. I was telling you to ignore people with small doses of treatment, but they're ignoring people who just have blocks with small ranges of responses. So this guy here is the probability of a positive treated minus controlled pair difference, conditional on the absolute value of that pair difference. Okay, and this shows up in Edgeworth expansions for signed rank statistics by Albers, Bickel, and Benzwet. Suppose you could have, this is a game, suppose you could have an infinite amount of data, but only at one absolute pair difference. You can have as much data as you want, but only at one absolute pair difference. What absolute pair difference would you pick? Well, it turns out that the absolute pair difference that you would want is the one which maximizes the ABZ function. Because at the maximum value of the ABZ function, the rate at which you're seeing positive pair differences can be maximum. And the bias magnitude gamma will produce a positive pair difference with probability gamma over 1 times gamma. So it's this guy that you want the maximum. You throw away the small ranges because they don't contribute positively to that. So let me show you a picture now of these are ABZ functions for match pairs. They all deal with the case we talked about. The expected treatment pair difference is half the standard deviation of a pair difference. The red line is what a bias of gamma equal to 4 would produce. 80% of the time it's positive. The black line is a normal distribution, favorable distribution. The logistic is the green, and the blue is a T distribution with 5 degrees of freedom. So what are you seeing? You're seeing down on the left, guys just don't want.
Because they're producing positive pair differences with probability less than 80%. Since they're producing positive pair differences with probability less than 80%, they don't produce enough so that you can distinguish them from a bias of gamma. If you look in the middle towards the end, right, you're seeing values above the red line, and those mean that you're seeing positive pair differences more than 80% of the time. You can't explain that bias of gamma. So you want to tailor a test statistic to look like that. So it's going to emphasize those values, which is what the Kluger-like guys are doing. In response to your question, the low dose people are like down over here. They're producing too few positive pair differences. The difference between a person who drinks 2 glasses a week, a person who drinks none, producing too few pair differences that are positive, who really overwhelm even fairly small values of gamma. So throwing them away is actually a good thing, just as throwing away the guys down at the bottom here.
Excellent example and discussion. I just wanted you to be aware that very high levels of HDL can be paradoxically associated with an increased risk of adverse cardiovascular outcomes. Have you heard that?
I haven't, but I am not entirely surprised. I have a little piece in Chance which says it's nice about the HDL, but survival actually isn't so wonderful for the people who are doing daily drinking relative to control. Actually, it's not that. It's that if you have 2 control groups, people who never drink and people who drink a negligible amount, right? What you see is if you merge the 2 control groups, people who drink daily look better than the merged group. If you split the 2 control groups apart, the people who drink very lightly look exactly like a few drinks a year. They look exactly like the people who are drinking daily, and the people who never drink look much worse. And if you look a little bit more deeply, you see the people who never drink are on all kinds of medications for all kinds of health problems, which say don't drink. So it doesn't surprise me that that's true. Thank you.
One last question.
Yes.
So, the block with the issue and the opinions of the conclusion was that since we have this other information or other studies that the temperature is not associated with drinking, that we could use that as a test for whether or not there is randomization. Right?
You can test anything, including in particular the randomization. What you most commonly see done is people say, I tested the randomization probabilities and they're not solvable. Oh my God. That's the standard thing. But you can also use them to test other things, right? You can test anything. You might as well do that and learn which states are plausible and which are not. In this particular example, some of the things that were worrying to us because we were getting sensitivity to bias were actually being rejected. So that improvement was compared.
Thank you, Paul, for a wonderful talk.
Thank you.